section 9.1, Determining Probabilities. We are going to start our discussion today of probabilities. You're going to see different pieces in this chapter come up again from what we did in the fractions chapter, coming up again from what we did in the decimals chapter. So both of those play heavily into this particular chapter's information. So to start with, we're going to talk about what probabilities are, and we need a little bit of vocabulary in order to do that. So the first thing we're going to refer to is something called an experiment. So certainly a scientific experiment is an experiment, but there's other kinds of experiments as well. Our general term is simply going to mean that it's activity whose results can be observed and recorded. Okay, so an experiment could be rolling dice. Experiment could be predicting the weather, those kinds of things, all right? An outcome is just the possible result of the experiment. So if we're rolling the dice, a possible result of the experiment is you roll a 2. If you're predicting weather, one of the outcomes could be that you predict it right. One could be that you predict it wrong, right? Or if you're predicting in terms of the rain, one outcome could be it rains, and the other one is that it doesn't, or something like that. The sample space is simply the collection of all possible outcomes. So let's keep going with our dice example. So if we did the dice example and we talked about sample space, what are the different possible outcomes, all of them, that would be in the sample space of rolling a regular old 6-sided die? 1 through 6. And let me show you actually how that would look as well. So a sample space is a set. So for those of you who've had number theory with me, or elementary math 1, we do the curly braces, and we write all of the outcomes. These are the outcomes we just referred to. Inside the curly braces, and we close it. That's a sample space, okay? And then an event is any subset of the sample space. So it's any smaller collection. So for instance, an event could be rolling an odd. An event could be rolling a 1. I mean, it might be very specific, or it might have a few things in it. Okay, so a sample space is just a smaller collection of the subset itself, the sample space itself. Okay? Theorem 9.1 is Bernoulli's theorem, or the law of large numbers, and it says the following. If an experiment is repeated a large number of times, then the probability approaches a fixed number. So, for example, let's just talk about flipping a coin. Okay, a plain coin, it's not anything out of the ordinary. You got heads on one side, tails on the other. All right, so if you flip a coin, what are the possible outcomes that you could have? Heads or tails? And on any given flip, what is the likelihood that you flip heads? 1/2. That's called the probability. So the probability of flipping heads on one flip is 1/2. Okay? But if you flip it several times in a row, you may or may not get half of them heads and half of them tails, right? If you flip it 10 times, you may not get 5 heads and 5 tails. Maybe it's 3 and 7. Maybe it's 2 and 8. Maybe you get 10 heads in a row. It's possible, right? But Bernoulli's law of large numbers says that if we flip it a bunch of times, I mean like 10,000 times, you're going to have about 50% heads, 1/2 heads, and 1/2 tails. That's what Bernoulli's law of large numbers says, is that over a large number, this is going to still be that same individual probability of flipping it 1/2 for for one coin getting 1 heads. All right, so what you're seeing in this calculation of probability is that the probability of event A happening is the number of ways that event A can happen divided by the number in the sample space. So let's just do a quick example of this with our dice example that I mentioned before. Let's say that event A, is that we flip a 2 or a 5. We're playing some game, and those are our desired outcomes. We really want to get a 2 or a 5 because it's sorry and we're going to land on top of trouble or something. We're going to land on top of somebody and send them home. Really want a 2 or a 5 to make that happen, okay? So how many ways can I get a 2 or a 5? 2 ways, right? I can get 1, 2, or 1, 5. So there's 2 different outcomes in the sample space that are what I want. How many, not of the sample space, of the event. How many items are there in the sample space of rolling this die, though?
6.
There are 6. So this would be 2 out of 6, and we will reduce it. Most of the time, there are occasions where we might not, but generally speaking, we'll reduce. So this is a 1/3 probability of getting the desired outcome. In this case, flipping a 2, or rolling a 2 or a 5.
Where did you get the 6 from?
Because it's a 6-sided die.
Oh, okay.
Yeah. So my sample space was the same sample space I had over here. That was 1 through 6. for a die.
Okay.
Yeah. All right, mutually exclusive events are events that have nothing in common. So if we talked about our die and we said event A was 2 and 5, and event B was 1, 4, and 6. Okay, so it doesn't have to include everything that's left, but just the things that, it can only include things that are not in set A. Then A and B would be what we call mutually exclusive. They have nothing in common. They're event outcomes that have nothing in common. All right, a couple theorems are what's coming next. Theorem 9.2. If A is an event and S is the sample space, then the probability of the event is between 0 and 1. If the probability of an event happening is 0, that's an impossible event. Okay? And if a probability of event happening is 1, that's a for sure thing. It's a certain event. But everything has to be between those. The 1 and the 0 are very similar to what we worked with in the last section with percentages, right? 0 means 0%. 1 means 100%. You can't have greater than a 100% chance of something happening. People use the language all the time, and they do it in jest. I do think that people really don't believe that they can have 110% of something happening, like 110% chance of something happening. But we talk about it like that sometimes. We're being funny, okay? But really, our probabilities are between 0 and 1. 0, it never is going to happen. 1 is for sure going to happen, okay? Everything is going to be somewhere in between those. So anytime you come up with a probability, it better be a number that's between 0 and 1. The probability event is equal to the sum of the probabilities of the disjoint outcomes making up the event. All right, so we're going to talk about our six-sided die again. We're going to consider the probability of rolling an even. Okay, so this P is not, it's not a function per se. It's not algebra. It's not multiplication either. It doesn't mean P times even, okay? This is saying the probability of, the word of is what's inserted in there, probability of rolling an even. Well, what this theorem above is saying is that that's the same as taking the probability of rolling a 2 plus the probability of rolling a 4 plus the probability of rolling a 6. Because you can only do one of those things. You can't have both of those things happen. You can't roll a die and it land on both 2 and 6, right? One die, I've got one outcome. So if I talked about the probability of rolling an even, the way that I would talk about it is I would say, well, what are the number of ways that I can roll an even over the number of my sample space? So what are the number of ways I can roll an even? 3. And the number of my sample space is 6. So let's do the right-hand side now. Well, what's the probability of rolling a 2? Well, what are the number of ways that I can roll a 2? 1 out of 6. How about number of ways I can roll a 4? 1 out of 6. And the number of ways that I can roll a 6? 1 out of 6. And the outcome is the same. 3/6 in either case. Okay? So if we have disjoint events, we can add their individual probabilities together.
So you said the number on top is the number of like possibilities.
It's the number of possibilities in our event.
Okay.
And the number on bottom is the number of total possibilities, period, in whatever situation we're talking about.
Okay.
Yes. All right, so mutually exclusive. What did that mean again?
But they don't have anything.
They don't have anything in common. So if events are mutually exclusive, then the probability of finding the union of their events is the sum of their probabilities. So again, I know some of you have had number theory and some of you haven't. So let me just talk briefly about this notation because this comes up in that class, this U in between. The U in between means either or things happen. Okay, one or the other. So my example before, let me flip over here. Here was event A and here was event B, and they are mutually exclusive, right? So the probability that one or the other of something in those events happening is Well, I just add them together. There's 5 of those items within those 2 events. There's no overlap, right? So it's 5 out of 6. And I could do it by adding them separately, like this as well. The probability of event A happening is 2 out of 6. And the probability of event B happening is 3 out of 6. So if I added those numbers together individually, I'd get 5 out of 6. And that's all this theorem is saying, is that if they're mutually exclusive, you can add their individual probabilities together, and that will work. Now, let me make sure that I don't have this coming up later. No. Okay, so let me make mention of the fact of what happens if they aren't mutually exclusive. So let's say that instead I had event A, and it was 1, 2, 3. We're still rolling our die, by the way. It's just an easy example to work with. And event B is evens. It's 2, 4, 6. So in this case, if I was wanting to know the union of these sets, what I would do is I would want to know everything that's in either set. And I'd list them all out. So somebody tell me what the list would look like. 1, 2, 3, 4, and 6. Right? That's what it would look like. Union just means you collect all of the things in either set. Maybe some of them are in both sets, maybe they're not, but you just collect them all. Okay? It's like getting married. When you get married, you get my stuff, I get your stuff. It's a union, right? We use the word union there to mean the exact same thing. All right, so the difference is that these 2 sets are not mutually exclusive. What do they have in common? 2. They both have a 2 in them. So if I found the individual probabilities, what's the probability of event A? Yeah, it's 3 over 6. What's the probability of event B? 3 over 6. What's the probability of the union? Yeah, it's 5 over 6. And that's not the same thing we would get if we added those individual probabilities together, right? So this idea of them being mutually exclusive in here matters, or it won't work. All right, a few of these all together now. Actually, not all together. We're about to get them all together. Theorem 9.5. If we talk about, again, a little bit of set theory, we have an event A. An event A complement means the things that are not in A. Okay? So if I did event A above, the same event that I wrote here above, event A, what would A complement be? Right, it would be 4, 5, and 6. It's just everything that is not in A. They don't overlap, right? If it's in one, it's not in the other, and so forth. Well, what this theorem says is that if I added the probability of A and the probability of A complement, I get back everything. If I add, and then these other 2 are just variations of it. All these are is subtracting the probability of A or the probability of A complement to the other side. Okay? So in other words, if I knew that the probability that it was going to rain today was 0.4, then what's the probability that it's not going to rain? 0.6. You guys do this all the time, right? It's just subtraction. It's just the percentage that's missing to make up 100%. That's all this theorem says, is that the probability when I talk about 2 things that are exact opposites, either it's in this set or it's in this one, then those 2 probabilities have to add up to 1, or 100% if you're thinking in terms of percentages. Okay? All right, this is just a list of all of the different probability facts. So this is your go-to list when you're trying to figure out what the details are with what's going on. And all of this is stuff we've said before. We'll run through it again. The first one, the probability of, we probably should talk about this notation. So those of you who've had number theory, do you remember what that notation is?
Like an empty set.
Empty set. So this is an empty set. So this is a set with nothing in it. So this is like, the infants that live at my house. There's none of them. I don't have any infants living in my house right now. My son thinks that we should have one. And when he saw that I bought a baby gift for somebody, he was very hopeful. And I had to say, no infants right now. No, we're good. So this is an empty set. It means something that there's nothing in it, okay? So if there's probability of the empty set, that would be 0. It is an impossible event. The second one, probability of S. S is the sample space. That's what we're using S for. So the probability of the sample space, that is the probability that something in the sample space happens, is 1. It's a very broad description. It's a for sure thing going to happen. Something's going to happen, right? You wake up in the morning, there's going to be some weather outside. There's a 100% chance of something happening out there. I don't know what it's going to be, but it's a 100% chance of something. Okay? It's all the possibilities. The third one, this is actually the very first one we discussed. The probabilities of everything else is somewhere in between 0 and 1. Between a 0 and a 100% chance that these individual events are going to happen. All right, these next two, not last two, but these two right here have this detail right here in it. It says the A intersect B is the empty set. This notation means they're mutually exclusive or they have nothing in common. Okay? We already talked about that. You just didn't see the notation for that before. So if the events have nothing in common, then the probability of the union is the probability of each individual piece added together. So if you look at the next one, it has something extra in it that the last one didn't have. It has this piece on the end, right? And it has this piece on the end because it doesn't have the fact that they're mutually exclusive in the middle. So I want to go back to the example that I had before where A and B weren't mutually exclusive so you can see how this plays out. This example at the top of the page where I had A is the set 1, 2, 3, B is the set 2, 4, 6. We knew that those individual probabilities were 3 over 6 and 3 over 6, right? Where do these two intersect? 2. So if I were to look at the intersection, so this A with the upside down U is an intersection. It means what they have in common. The value that they have in common is just the value 2. Oh goodness, how did I do that? Thank you, Leah. Let me fix it. All right, better. Not perfect, but better. Okay, so the thing that they have in common is 2, right? What's the probability of that then? What's the probability of this happening? I've heard 2 over 6 from a couple people. Think again. 1 over 6. I know that we've got numbers playing different roles in here. But rolling a 2 is a single side of a dice, right? One side of a dice, there's 6 sides total. So the probability of rolling a 2 is a 1 out of 6 chance. Okay, so what this theorem says, I can do is I can take the probability of event A, that was 3 over 6, plus the probability of event B, which is 3 over 6. And I can subtract the probability that both events happen, which is 1 over 6. Does anybody remember this? We had a very similar formula to this in number theory. Does anybody remember why we subtract the 1 over 6? What are we doing?
Taking out that common 2 that they have.
We're taking out what they have in common, right? Well, that seems sort of funny. Why would we take out what they have in common?
Because that would be intersecting.
Okay, that's the intersection, but why are we taking it out?
It counts it twice. If
You got it. Good job, Taylor. It counts it twice. Right? When we were over here, we counted the 2 twice. I counted the 2 when I counted it in the probability of A, and I counted the 2 when I counted it in the probability of B. I double counted it. So the reason that I removed the intersection once is because it removes the double counting that I did. And that's exactly what this formula does. It removes the double counting. Now, if you think about it, this formula will work just fine right here as well. No problem. Because what's the intersection on that one that's got the arrow next to it? What's in it? What's in the intersection? Nothing, right? It says that they intersect in the empty set. They have nothing in their intersection. So if I were trying to do something where they didn't have any overlap, what would happen at the end of this equation? What would the probability be? 0, right? The probability that I have a child and my sister has a child and it's the same child is 0. We don't have any children that we share, right? It doesn't work. So if you're trying to do something that has no overlap, you just get a -0 at the end. Okay? The last one we talked about before as well, the probability of the complement is 1 minus the probability of the event, right? The raining, not raining situation kind of thing. All right, we desperately need some examples because I don't know about you, but I'm tired of listening to all of the theory behind it, right? Examples help us quite a bit. All right, so we're going to start with a deck of cards. And the first thing we're going to do, because I know not all of you are probably as familiar as everybody else with decks of cards, is we're going to run through a few facts. So if you don't know these facts or if they're sort of not fresh in your mind, you're probably going to need them at some point in this chapter, so jot some of these down. How many cards are there in a standard deck of cards? 52. We're not doing jokers. Yeah, 52. How many red? 26. How many black? 26. Okay, good deal. What are the 4 suits? Hearts and diamonds, those are the red ones, right? And then spades and clubs, those are the black. Okay, so how many hearts are there? 13. How many diamonds are there? Clubs and spades. Okay, so there's 13 of each suit. Very good. All right, so let's talk about the cards' value on the cards. So what are the values you see on the cards? Some of them are number cards. What's the lowest number card? A 2 is our lowest number card. What's the highest number card? There's a 10. Okay, so it's from 2 to 10. Those are my number cards. What about face cards? What are those? Jack, Queen, King. And your book views ace as neither one of those things. Okay, ace is not a face card. It's not a number card. Okay, so anytime you hear it referring to face cards, it means Jack, Queen, King. That's all it means. Okay, so ace does not get included in either number cards or face cards. How many of each value card are there? In other words, how many 10s are there? How many queens are there? 4. There's 4 of each of the value cards. Okay, that's all I can think of right now. If we come across something I didn't say, we'll introduce it at that point. That's pretty good, though. All right, so what we're going to do is it says, consider drawing a single card from a standard deck of cards and determine which of the following are equally likely. Okay, so what we're going to do is we're going to figure out what the likelihood is of each of the events that are listed, and then we're going to compare those events to decide, are they equally likely? So, face cards. How many face cards are there? I think there's 12. So how'd you get 12, Catherine?
Because there are 3 face cards in each suit and there's 4 suits.
Right. There's 3 face cards in each suit, Jack, Queen, King, and there's 4 of each suit. So like there's 4 jacks, 4 queens, and 4 kings, right? So there are 12. So the probability of the face card, we'll just write it next to it. This right here is 12 out of how many? 52. All right, not a face card. How many is that? 40. What's the quickest way to find that? Yeah, 52 minus the 12. And in fact, when you did 52 minus 12, do you know what property you used? The complement. You used this property down here. When you subtracted 52 minus 12, you used that property. Okay? Good deal. So is it equally likely to draw a face card versus not a face card? No. These are not equally likely. Clubs. How many clubs are there? Out of 52. How many diamonds are there? Out of? Yes. And how many, what's over next? Hearts are there? Yes. And spades? All right. How about these? Are these equally likely? Yes. is equally likely to draw any particular suit? How many black?
26.
Good. And out of how many total? 52. How many red? Out of? Are these equally likely? Yes. All right. King, queen, jack, ace, even, odd. Oh my goodness. How many king, queens? How do we have for these? Kings. 4 out of 52. Queens? 4 out of 52. Jack? 4 out of 52. Ace? 4 out of 52. So it's looking good. And then we hit even. How many evens are there? There are 20. Okay, so I see some of you counting on your hands. So the smallest even is a what? So you have 2, 4, 6, 8. There's 4 evens times 4. Wait, 10. I'm sorry, I left out my 10. I'm like, that's not right. And a 10. So there's 5 evens times 4 suits. So there's 20 even cards. How many odd cards are there? That one's actually 16. You're right. So on that one, I have to start with what number? 3. So I have 3, 5, 7, and 9. There's only 4 of those times 4 suits. So that's 16 cards. All right. Are these equally likely? No. They almost were until we got to the end, right? But then they weren't. So these are not equally likely. All right. Let's take a look at something from a different perspective. Okay, not looking at dice or cards now. A Civ class is composed of 21 men, 34 women. There are 22 education majors, 13 religion majors, 12 science majors, 5 English majors, and 3 math majors. Assuming that no one has a double major, that's an important assumption, right? Because otherwise they'd get double counted somewhere. So we're assuming there are no double counts. So assuming no one has a double major, if a single student is chosen at random, what is the probability that the student is ... Okay, so what is the probability that a student is female? 34 out of what? 55. So where did 55 come from? Excellent. So you guys decided to add the men and the women together and you get 55. Good first start. Okay. Now, 34 and 55, if they can, we're going to reduce them. Can they be reduced? No, they can't. 34 is only divisible by 2 and 17. And 55 doesn't do that. So, how about science majors? 12 out of 55. So again, can that be reduced? No, it can't be, because 55 only divides by 5 and 11, and 12 doesn't divide by either of those. All right, an English major or a religion major? So what are we going to do to find that? Right, here's the English and here's the religion. So if I add those together, what do I get? 18 out of 55. Do those reduce?
No.
Still not going to work, right? No 5s or 11s in 18. Last one says, neither a math major nor a science major. Now, there are a couple of ways to do the problem. So I want you to take just a second and figure out what you would do for this problem. Go ahead and write it down, what you believe the answer should be. Think about how you got to that point. Okay, volunteer to tell me how you got there. Leah.
I added together the math and science majors and I subtracted them from 55.
Okay, did you guys hear her? So she added the math and the science. So there's 3 math and 12 science, and you got 15. And she subtracted 15 from 55. Does that work? Yeah. What does that give us? 40 over 55. Did anybody do it differently?
I added up all the other majors besides science.
Okay, so Catherine, you added up, hang on. the 22, the 13, and the 5. Does that sound right? Okay. And because each of these are not very many steps, it's probably about, half a dozen one way, 6 the other, right? I mean, we pretty much did the same thing, same number of steps, took the same amount of time. What if there had been a whole bunch of things to add up in one of these categories or the other? Would it have been practical to use a different way, perhaps? Yeah, it might have been. So it's good to be aware that there's more than one way to solve problems sometimes, because sometimes the way you think to solve it might be a lot more complicated than if you stop just a little bit to think, is there a better way to do this? All right, 40 out of 55, though, does reduce 8 over 11. All right, any questions on that one? Okay. A student claims that if a fair coin is tossed and comes up heads 5 times in a row, then, according to the law of large numbers, the probability of tails on the next toss is greater than the probability of heads. What is your reply?
More than just like very many times.
Okay, so there's one issue that this isn't very many times, but so let's say then, Madison, that we change it. Let's say that it came up heads 5,000 times in a row. What would we say then?
You could say that it doesn't matter how many times it's already came up one side, like the next one could still be anything, because it's just, like, I don't know.
Yeah, they're talking about the next one. They're not talking about like overall.
Okay, so each of these individual coin flips, and we will get this vocabulary, I think it's a 9-2, is what we call an independent event. It doesn't have any bearing on what happened the last time, right? When I flip a coin, it doesn't matter what happened the time before. I still have the 50-50 shot. I will tell you, though, if I had 5,000 heads in a row, I would probably wonder if the coin was fair. Wouldn't you? Yeah, I would too. But it still wouldn't change the outcome whether it happened or it didn't happen. So a couple things we're going to write down. So I think it's worth mentioning that the law of large numbers doesn't apply. And it doesn't apply for 2 reasons. The first one is what Madison mentioned, is that 5 is not large. Okay? If you have 5 children, I would say it's a large family, but that's not what we're talking about, right? 5 is not a large number. However, even if it were a large number, these are independent outcomes. So we'll say it this way, flipping a coin results in independent events. And since we haven't defined that, I'll clarify. Independent events means, let me say it this way, one outcome has no effect on the next. So there's 2 kind of issues at play here. If all we said was that 5 is not large, it really doesn't get to the real problem in this. You guys see that? I mean, it is a true statement. We wouldn't apply it for that reason as well, but it really doesn't hit home what's really going on here. All right, let's take a look at another one. What happened? I'm missing number 4. Fabulous. Okay. So I don't have a slide number 4. You guys do, so I'll draw the picture and I'll read from my slide what it is. All right, it says, the following spinner is spun 100 times. So you have a spinner and it looks something like this. And this has a 1, 2, 3, and 4, and it draws a spinner out as though it's going like this. So there's, the little spinner guys going around. The spinner is spun 100 times. Joe claims that the number 4 will occur most often because it has the greatest area of space on the spinner. What would you tell Joe about his conjecture? Conjecture really just means guess. That's what he believes will happen. What would you tell Joe about his conjecture? And then what is the probability that 4 will occur on any spin? Okay.
The angle of it is not greater. It's just like, I don't know how to say it, but it won't affect.
Okay.
Like the overall size of the section is bigger, but the spot where the spinner is going to be in is the same size in each.
And that's the angle you're referring to, right, Madison? Okay. So he's thinking about this picture in kind of a wrong way, right? He's thinking about the space that the section takes up and not the angle that it's spinning through. And when the spinner is spinning, it's the angle that matters, right? Okay, so let's write some of those ideas down. The spinning is unrelated to the area of the region. It is related to the angle the spinner passes through. All right, so that's sort of answering the issue of what would we tell him about his conjecture. The next part of the question says, what is the probability that 4 will occur on any spin? 1/4. Why?
Because there's 4 altogether spots, and you can hit a 4 at one time each spin.
Okay. I agree with you because of the particular picture we're discussing, so let's discuss why that actually works here. There's 4 regions. Why is it going to be 1/4 though? It's not exactly because there's 4 regions. Okay, and I don't think you mean section, I think you mean angle.
Yeah, each angle comprises.
Yeah, it's because these angles have equal measure, right? Each angle is the same as the other ones. So this is probability of 4 is 1/4 because the measure of the angle of each section is equal. And there are 4 regions or sections. So it's the angle that matters, right? It's the angle that matters, and all of those angles are the same, and there's 4 of them. Does that make sense? Okay, so the other version of this question, example 5 says, what if the previous question posed was the image of a dartboard? Not a spinner, but a dartboard. Would that change your reply to Joe?
Yes.
Yes.
Because it does matter on the area on this one, because if 4 is the biggest section, you're most likely, the probability of hitting 4 is going to be a lot higher.
Right? So it's not just the picture, it's what you're dealing with it, right? I mean, it really makes a difference. It really does. All right, so yeah, it does. So if this is the situation instead, is his conjecture correct? Yeah, okay. So then his conjecture is correct. Since region 4 has the most area, it has the highest probability. Could we find that probability? But could we find it with the information we're given? No, we really couldn't find that particular probability with the information we were given. If we actually knew the lengths of these segments, they're called chords that are cutting through our circle, we would have the ability to do that, but we aren't given that information on this particular diagram. So we couldn't actually say, oh yeah, it's a 0.6 probability or something like that. We don't know that for sure, okay? All right, any questions on those? All right.